Okay, let's unpack this. We're diving deep into a stack of your sources today.
Yeah, all about four-sided shapes, quadrilaterals.
Right. Think of this as your kind of express route to understanding these, well, fundamental geometric building blocks.
Mm-hmm. Mm-hmm. Our mission really is to pull out the most important nuggets from the material you've shared.
And figure out what makes these shapes tick. So starting right at the basics.
Meh.
Based on the material, what's the absolute core definition?
Well, it's pretty simple, actually. The sources just define it as a closed polygon with four sides. That's the baseline.
A closed shape, four sides.
Got it.
And the sources mention its key parts too, right? Beyond just the sides.
Exactly. You've got those four sides, naturally.
Yeah.
But also four vertices, the corners,
Okay.
four interior angles inside the shape, and two diagonals connecting opposite corners.
Right, cutting across the middle. Now, there's one really key thing about any quadrilateral that your sources seem to emphasize, especially with the angles.
Yes, and it's super useful. Some of those inside angles, the interior ones, it's always 360 degrees, no matter the specific shape.
Always 360, like four right angles put together.
Precisely. That's a foundational piece of knowledge the sources give us right away. A constant.
That 360 rule is a great starting point. So from that general idea, your sources then branch out into different types, getting more specific.
Uh-huh. Based on specific properties, like parallel sides, for instance.
Okay, so let's start with the sources do. The trapezium.
Right. The definition provided is quite clear. A trapezium has just one pair of opposite sides that are parallel. Only one pair.
And the material mentions a special version too.
Yeah.
The isosceles trapezium.
It does, yeah. That's where the non-parallel sides are equal in length.
Oh, okay.
And the sources note this gives it some nice symmetry, like the base angles come in equal pairs, and the diagonals end up being the same length too.
Interesting. Okay, so building on that idea of parallel sides, the next shape the sources detail really snips it up. The parallelogram.
Yeah, this is a big one. Here, both pairs of opposite sides are parallel, not just one.
Both pairs. And that changes things quite a bit, doesn't it? What properties pop out according to the sources?
Some really crucial ones. Opposite sides aren't just parallel, they're also equal in length.
Okay, equal length too.
And opposite angles are equal. Plus, and this is very handy, the diagonals bisect each other.
Bisect, meaning they cut each other exactly in half where they cross.
Exactly. Right in the middle.
And your sources even offer a kind of shortcut for proving something is a parallelogram.
They do, which is efficient. They say you don't always need to check everything. If you can just show that one pair of opposite sides is both equal in length and parallel.
Just one pair doing both jobs?
Yeah, that's enough. The sources confirm that's sufficient proof it's a parallelogram. Kind of neat.
Okay, so once we establish we have a parallelogram, the sources show how adding more rules creates even more specific types, like the rectangle.
Right, so a rectangle IS, a parallelogram, but with an extra rule. All four angles must be 90 degrees.
Right.
Right angles.
All corners are square.
Exactly. And because of that, the sources add its diagonals become equal in length. That's a consequence.
And then there's the rhombus, also a parallelogram.
Also a parallelogram, yes. But its extra rule is about the sides. All four sides must be equal in length.
So rectangle's about angles, rhombus is about sides.
You got it. And for the rhombus, this equal side length gives its diagonals a different special property mentioned in the sources. They still bisect each other, but they intersect at 90 degrees. They're perpendicular.
Perpendicular bisectors. Okay, now, this is where it all seems to come together, doesn't it? The square.
Ah, the square. Yes, the sources really position this as the grand finale in a way. It ticks all the boxes.
How so?
Well, it's a quadrilateral, obviously. It fits the definition of a trapezium. It has at least one pair of parallel sides. In fact, it has two. It's a parallelogram.
Right.
It's a rectangle because all its angles are 90 degrees. And it's also a rhombus because all its sides are equal.
Wow, okay. So it inherits everything.
Pretty much. All sides equal, all angles 90 degrees. And its diagonals. They get both special properties, they're equal in length, and they bisect each other at 90 degrees.
It's like the perfect intersection of a rectangle and a rhombus.
That's a great way to put it, yeah. That's what the properties outlined in the sources lead to.
So we've walked through the definitions and properties, pulling this all straight from the material you provided. But why does this matter? Why dig into these distinctions?
Well, it matters because these shapes are literally everywhere, in buildings, bridges, furniture, even art.
True.
Understanding their precise properties, like how parallelogram diagonals work or why a rhombus's diagonals are perpendicular, helps us see why things are built the way they are. It's about stability, design, engineering.
So the properties described in the sources have real-world consequences for function and form.
Absolutely. They're the geometric rules governing how things fit together and behave.
Okay, so we've done a quick but hopefully insightful deep dive into quadrilaterals today. Basic definitions, specific types like trapeziums, parallelograms, rectangles, rhombuses, and squares, all based on the material you curated for us.
Following the logic from the sources.
And this kind of brings up a final thought, doesn't it? When
Yeah.
you, listening, look around today, maybe at a window, a door, floor tiles, a picture frame, can you start to identify which specific type of quadrilateral it is, based on these precise definitions and properties we've pulled from your sources?